Every textbook says it's dead, too small to stay hot. Fuel burned out eons ago. Internal fire gone long before life on Earth even got started. That was the clean story of Mars. A small planet that cooled fast, lost its magnetic shield, and got its atmosphere stripped away. Simple, elegant, and now much harder to defend. Because the newest picture of Mars's interior suggests something that does not fit the dead planet stereotype at all. Deep inside Mars, above its iron core, there may be a thick layer of molten rock, roughly 90 miles thick, wrapping the core like a hidden seam of liquid. That is not a minor geological update. That is a direct challenge to the timeline we use to explain when Mars lost its magnetic field, when it lost its atmosphere, and how long it could have stayed habitable. To understand why this is disruptive, you need the harsh geometry of planets. Small worlds bleed heat. Earth is big enough that it can hold internal heat for billions of years. Mars is smaller, so its heat should escape faster because it has more surface area compared to its volume. So for decades, the default assumption was that Mars should have settled into a predictable stack early on. A crust on top, a rocky mantle below, and a liquid iron alloy core at the center. But crucially, for a planet to run a global magnetic field, it needs a dynamo. A dynamo needs energy and motion. It needs the interior to transport heat in a way that drives convection, especially in the core. No vigorous convection, no global magnetosphere. And without a magnetosphere, the solar wind can erode the atmosphere over time. That's the classic chain. Heat flow, dynamo, magnetic shield, atmosphere. So in 2018, NASA landed a stethoscope on Mars. InSight. Its job was simple to say and brutal to execute. Listen to Marsquakes, read the waves, and infer what's happening deep underground. At first, the results seemed to support the standard story. Early interpretations pointed to a surprisingly large, relatively low-density core, suggesting a core enriched in lighter elements. But then came the problem. The numbers were difficult to reconcile cleanly with other constraints, like Mars's rotation and how its interior responds. And after a major impact event in 2021 and a deeper reanalysis of seismic phases that travel near the core mantle boundary, a different structure emerged. The key idea is this. Seismic waves don't just tell you what is solid or liquid. They tell you where the wave slows down dramatically. And the updated models suggest that what was once interpreted as the boundary of the core may actually sit above a molten silicate layer at the very base of the mantle. In this picture, Mars still has a liquid iron alloy core, but the core is smaller than some earlier estimates, and the layer above it includes molten, iron-enriched silicates. That molten layer is the part that makes Mars harder to explain, because once you put a thick molten silicate layer between the core and the overlying mantle, you change how heat moves. You may alter how efficiently the core can lose heat. You may alter how the mantle convects, and you may change the lifetime of any core-driven dynamo. This is where the contradiction becomes unavoidable. We have strong evidence that early Mars did have a global magnetic field. We see the fingerprint of that ancient field locked into magnetized crustal rocks, especially in the southern highlands. Mars today has no global field, but the crust remembers a time when the dynamo existed. So the story now has a new tension. If a molten basal layer has been sitting there for a very long time, how did Mars sustain the heat flow conditions needed for a dynamo early on? And if that layer formed later, what created it? And why would it appear after the dynamo era? One possibility is that the layer is a relic of early differentiation. Mars likely had an early magma ocean. As it cooled, the chemistry could have separated in a way that left an iron-rich layer near the bottom of the mantle that stays molten far longer than the rest. Another possibility is that we are underestimating how complex Mars's thermal evolution is, especially how layering can throttle heat flow in ways that aren't intuitive. And here's the part that makes this a real scientific mystery instead of a neat headline. Some versions of this layered interior picture imply that the magnetic signatures recorded in the crust may need additional explanations beyond the simplest core dynamo story. That doesn't mean the magnetic field didn't exist. It means the interior story is no longer a single straight line. It is branching. Now add the second consequence: volcanism. If Mars's deep interior retains more heat than we assumed, it helps explain why Mars can still look geologically alive in places. There is evidence consistent with very recent volcanic activity on Mars, possibly within the last 50,000 years in regions like Cerberus Fossae. That is a blink of an eye in planetary time. So Mars may not be dead. It may be stifled. Heat present, but not expressed the way Earth expresses it. A planet with a warm interior and a cold-looking surface. And that changes how we think about habitability. Because the classic picture of early Mars, the rivers, the deltas, the ancient lake beds, depends on a climate window that lasts long enough to matter. A magnetic shield is not the only factor for habitability, but it matters for protecting an atmosphere over long timescales. If the magnetic field window was shorter than we thought, then blue Mars becomes a narrower chapter. And that is the uncomfortable question this new interior model raises. Was Mars ever truly Earth-like for a long stretch, or were the most Earth-like conditions brief, unstable, and easy to lose? This is why the new result is not just a geology update. It turns Mars into a harder case. A planet that looks simple from orbit, but hides complexity at the deepest interface. A molten layer where we did not expect one. A core whose size and density shift depending on how you interpret what the seismic waves are actually sampling. And the bigger lesson is brutal. We can no longer treat Earth as the instruction manual. Mars is not a smaller Earth. It is a different machine. One that may have developed a deep molten seal that rewrote its thermal fate. So when people say Mars is a dead world, the honest reply now is define dead. Because a planet can lose its global magnetic shield, lose most of its atmosphere, freeze its surface, and still hide heat and liquid rock deep inside. Mars just got harder to explain because the simplest story no longer fits all the evidence at once. And that is exactly why it's worth studying. Because if we can't fully explain the fate of the planet next door, we should be very humble about claiming we understand the life cycle of rocky planets everywhere else in the galaxy.